start?
Yes, please.
Okay. So good morning, everybody. This is the second session of the Attosecond conference. And then we will have 4 speakers at the second session. Francesca Calegari from DAISY and University of Hamburg from Germany. Ladislav Nagy from University of Cluj, Babes-Bolyai, Romania. Mirit Dudovich from Weizmann Institute, Israel, and Morgan Vacher from University of Nantes, France. So we should, the first speaker will be Francesca Calegari, and the title of her presentation is Real-time Tracking of the Electron Dynamics in Complex Molecules.
So, good morning, everybody. Thank you very much for the nice presentation. I just would like to start my laser pointer. As a vice chair of the Attochem action, I'm very happy to see the very high participation to this meeting, and I also hope at some point to meet you all in person and not only virtually. So today I would like to show you our activities on, let's say, the use of attosecond pulses for tracking the electron dynamics in complex molecules, which is the focus of my group in Hamburg. The reason why we look at extreme time scales, we heard already a bit in the first session, which was already nicely introducing the use of attosecond pulses for the investigation of electron dynamics in molecules. But I would like also to give a further motivation for doing this. I mean, why do we have? Why would you like to look at the extreme time scales? So what happens right after the light-matter interaction? So well, I would like just to show a very nice example, which I like very much. This is the DNA photoreactivation after damage from absorption of UV light. So the absorption of light is creating a damage in the DNA, and this is resulting in the pair of the pyrimidine bases, so it creates a pyrimidine dimer. But light can also repair DNA, and this is done by the photolyase enzyme. As you can see here, it's quite a complex molecule. The repair happens in a chain of events, which starts with an electronic rearrangement occurring in the HDF complex, which is then resulting in an energy transfer to the FADH charge donor complex, which is then transferring electrons to the pyrimidine dimer and finally breaking this bond and repairing the DNA. So as you can see here, actually, this very complex biological functionality, which is the reactivation of the DNA, is starting with an electronic rearrangement, so with a very fast process. What we would like to see is, first of all, if we can reveal the role of the electron dynamics in complex processing occurring in processes occurring at longer time scales. But we don't want only to watch, we also want to control at some point properties emerging, new properties maybe emerging at the level of electrons. This is our dream in a way. So we started our investigation of complex molecules looking at this process dubbed charge migration. We heard already about this from the talk of Fernando Martin. This was also mentioned later on. So I don't want to spend too many words about this process, but basically here, after sudden ionization of a molecule, it is expected that the charge is moving very fast, oscillating back and forth on the molecular backbone, and Attosecond technology provides a way to follow this ultrafast dynamics. So the way we wanted to look at this process was to send a sequence of pulses in this pump and probe approach, which has also been mentioned before. So we send an XUV attosecond pulse with a duration of approximately 200 attoseconds, followed by an infrared probe field with a few femtosecond duration. And we measure the ion yield. This was also mentioned by Fernando. Our observable are ions created at longer time delays. But we anyway can see some of the initial dynamics because we have very short time delays between the prompt and the probe pulses, and this can affect the creation of ions, so such that in the ion yield we can reveal the presence of a fast dynamics. And this is what happened in our measurement in amino acids, and here we observed charge dynamics between different functional groups of the molecules. This was very preliminary and was somehow motivating us to further investigate complex molecules with the Attosecond technology. So today I would like to show you other examples of what we do with complex targets. I will see if I will manage to go through all this list, but I really would like to show you our recent results in nucleobases, and then more and more complex molecules later on. So let me start with the nucleobases. So we decided to study DNA nucleobases after the absorption of 2030 UV light, because actually when ionizing radiation is sent in our tissue, then it's ionizing an avalanche of secondary electrons, which is then impacting on our DNA and damaging the building blocks of the DNA. These secondary electrons have an energy which is peaked around 2030 eV, so the energy range that we can access with our attosecond pulses. Although the investigation of photon absorption and electron attachment are very different, we could investigate what's happening to the basis, what is the relative stability in this energy range, and if there are any electronic processes occurring that might be taken advantage of when interacting with such light pulses. So we were investigating, in this case, more specifically adenine, which is one of the 4 DNA nucleobases. And what we immediately observed is that after XUV ionization, the molecule is fragmenting quite a lot. So as you can see here from the mass spectrum, it's quite rich. It's 81% of the mass spectrum is composed by fragments. And therefore, this indicates quite a low photostability of the molecule. So the radiation is indeed inducing damage, what we call damage. What we can do experimentally is basically to, again, perform a measurement as I was showing before. So to send an XUV attosecond pulse to ionize the molecule, and then an IR, few femtosecond IR probe pulse to basically monitor the dynamics we have initiated in the molecule. What we measure, again, is this mass spectrum. I just want to go one step back. So we measure this mass spectrum, and we can integrate each individual ion. So we have a ion yield as a function of the pump probe delay. As you can see here, in green I show some of the large fragments, and in blue some of the small fragments resulting from the molecule. And this is basically the pump probe delay. Here you can see that at 0 time delay, the large fragments are dramatically reduced, while the small fragments are increasing in terms of yield. And this is kind of expected because when you send your IR probe pulse, you basically deposit a further amount of energy in the molecule. So you do expect to further ionize, so to further fragment the molecule in smaller and smaller fragments. So actually, this is not helping in the stability of the molecule. It's actually making it worse. But something that we have observed very nicely is actually that by sending the IR probe pulse, we also observe the presence of the adenine dication. So this is the intact molecule. This is not present in the case of the XUV only ionization, and it's showing up only when we send the IR probe pulse. And the other characteristics of this ion is that it's coming with a small delay with respect to the other fragments. So it's coming at 2.3 femtosecond approximately later than the ionization triggered by the XUV pump pulse. This is actually quite interesting because we are inducing a sort of stabilization of the molecule. So just to summarize the interpretation we have given to this process. This is actually based on an electronic correlation effect, as was explained by Frank before. So when you ionize the molecule with an XUV pulse, you indeed can involve these correlated states, and more specifically, you can trigger a shake-up process from which, after the ionization of an electron from the XUV, another electron is filling the vacancy and promoting a third electron to the valence of the molecule, where our IR probe pulse now can easily ionize, so creating this dication and stabilize the molecule. So this is a sort of mechanism based on an electronic rearrangement, which allows us to stabilize the molecule. We collaborated with the group of Angel Rubio in Hamburg and with the group of Gianluca Stefanucci and Enrico Perfetto in Rome to better understand the theory behind this stabilization of adenine. And before we have performed, they have performed a simple calculation based on the rate equation, just to evaluate the transition time of the shake-up states involved in this process. And as you can see, there is a green state highlighted here. There's a LUMO +6, which has a transition time about 2 femtoseconds, which is compatible with what we observe in the experiment. This has been further validated by more complex calculations based on a non-equilibrium Green's function. And as you can see here, although many of the shake-up states, they are suddenly populated, so this is the state occupancy of those states, there is this LUMO +6 that indeed it takes some time to be populated. And so this seems to play a major role here, because we have to wait for the population of this state in order to enhance the absorption of the IR probe pulse and stabilize the molecule. And this is further confirmed by a more complete calculation, including the IR probe pulse. Here is the evaluation of the LUMO +6 depletion, meaning that we have an absorption of this IR probe pulse, and so the creation of the dication. And as you can see here, this is actually the absorption as a function of the pump probe delay. The absorption is not maximal at 0 time delay, but indeed it's increasing with time. And if we integrate this as a function of the pump probe delay, we obtain a curve which is rising in time, which somehow match with the curve we have obtained in the adenine 2+ ion yield, indicating that indeed the observed time delay is due to the gradual population of this shake-up state, which is very important in this stabilization process. More details will be provided about this experiment also in the talk of Eric Masson on Friday. I just go very quickly to a second example, which is the investigation of the presence of a gigantic plasmonic resonance in C60. C60 is actually a very large molecule compared to what I was presenting before. It has a very nice signature, around 20 eV. Indeed, you can excite a collective oscillation of the charge around the ionic cage. And this collective oscillation is actually giving rise to a relatively broad resonance, as you can see here. This is called the, let's say, giant resonance of C60. Something that we wanted to see was the signature of the presence of this resonance, so this collective motion of electrons in the photoemission. It is indeed possible to track with Attosecond technology the presence of resonances with measuring photoemission delays. And this is schematically represented here because when an electron is ionized, is actually not ionized with instantaneously, but there is a delay associated to the ionization, and this delay is actually called delay, and is due to the scattering of the electron wave function in the potential. The scattering potential could be simply the Coulombic potential. This is already originating some delay. But more specifically, if you have a resonance, then this is inducing further delay because your electron is actually scattering in a more complex potential. In the case of C60, you would expect to have a sort of screening potential, which is changing in sign across the resonance. And this is actually resulting in a delay, which is expected to have a change in sign. So it's sort of a screening and anti-screening effect over the photoemission of the electron. And this is due to the triggering of a collective motion in the molecule. The way we can measure this time is, again, sending a sequence of XUV plus IR, but we measure this time the photoelectrons. So Fernando would be happy about this, that we can also measure photoelectrons as a function of the delay between the two pulses. This technique is actually called streaking spectroscopy. The photoelectrons energy emitted in time is following the shape of the vector potential of the IR streaking field. But if an electron is emitted with a certain delay, then the streaking trace will result with a certain delay, which is including both the contribution of this Wigner delay that I was describing, and also the laser Coulomb coupling effect, which is basically the streaking field interacting with the asymptotic tail of the Coulombic potential. The way we did this experiment in collaboration with the group of Matthias Kling from LMU and MPQ in Munich is actually to detect a photoelectron emitted by the XUV in the presence of the streaking field with a VMI spectrometer, so velocity map imaging detection. Here you can see a typical photoelectron angular momentum distribution. If you integrate over a small angle here, then you get these typical streaking trace. Then you can do a contour analysis, contour plot analysis of the streaking trace, and therefore extract the delays of the photoemitted electrons, as you can see for C60. We actually have contribution in this delay, as I said, of different things. So not only the Wigner delay, but also the laser Coulomb coupling. So we need a sort of reference to cancel this contribution. The way we did that was to inject also neon, and so to perform a simultaneous experiment in neon, and to use it as a reference. So here you can see the delay of the photoemitted electrons in neon and in C60. Already you can see that there is a very different behavior. So we would expect to have some signature coming from the collective motion in C60. If you make the difference between these two trends, then basically you would be able to cancel the contribution of the laser Coulomb coupling, which is expected to be similar in the two cases. Then we are left with the Wigner delay of neon, which it's well known, can be easily calculated. It's also pretty flat in this energy region. Then we have the Wigner delay of C60, which is expected to be basically induced by the presence of this collective motion, this gigantic resonance, as well as another dipole contribution, because the presence of the IR field itself is also inducing a collective motion, and this is resulting in a delay in the streaking trace. So we actually have two contributions for the C60. This is the result of the subtraction. So this is actually, the green line is the experimentally retrieved trend. And as you can see, we also are preliminary trying to fit this trend with some calculations, although not really easy for C60. And basically the blue curve and the red curve indicate calculation in the presence of the IR field only. So this is the IR-induced dipole contribution and the XUV plus IR. So in this case, we activate the plasmonic resonance induced by the XUV. And so we can see that actually at the moment, the IR contribution alone is pretty much well fitting the experimental results, except for the very low energy region, where maybe we can see more signature of the Wigner delay, but this is still an ongoing investigation. Okay, more details also will come about these results in the talk of Bisbas on Friday. Another result we have obtained recently is investigation of time resolved investigation of chirality. This has been done with a new experimental apparatus, which is indeed using the generation of ultra-short UV pulses. Why have we moved our interest towards the UV spectral region? Well, until now we were mostly investigating a molecule ionized by XUV radiation, but as you all know, XUV is not reaching our basically the Earth surface because filtered by the atmosphere, while the UV radiation is penetrating and is actually, as I was mentioning at the very beginning of my talk, is responsible for damage and the activation of many photobiological and photochemical processes. So we have developed a new beamline recently, which is now combining our XUV pulses with ultra-short UV pulses. We have demonstrated the generation of sub-2 femtosecond UV pulses using an experimental approach, which is similar to what Katerina was presenting. So again, using a chip. I have no time to present all the details about this, but if you are interested, we can also discuss later in the other session. In the case of chiral molecule, we were actually combining the UV pulses with the IR pulses. So we can also switch off the XUV generation, and we can combine the few femtosecond UV pulses with the few femtosecond IR pulses as well. So this is what we were exploiting for the experiment in the chiral molecules. Why chiral molecules are interesting? What are chiral molecules in the first place? So as many of you know, chiral molecules are molecules with two enantiomers, as it's schematically represented here. Enantiomers are basically non-superimposable objects like our hands. And chirality is actually very important because, for instance, if you think about all the living organisms, we have remarkable homochirality there. So all the amino acids, for instance, has a precise chirality. Life is based on a precise chirality. And in pharmacology, for instance, a molecule which is used for heal a disease can have an enantiomer which has a toxic effect. So it could result to be actually lethal. So if the pharmacy is not selecting properly the enantiomer, then it could obtain exactly the opposite effect. So this is actually very, very important. The way one could probe the chiral response of a molecule is actually to use another chiral object. And for instance, we can use circularly polarized fields, which are also chiral. One way is to measure the absorption of circular fields. And this is called circular dichroism, but this is providing quite a weak signal. Therefore, there is another way, which is named photoelectron circular dichroism, where you can measure the photoelectron ejected along the propagation axis of the laser, as you can see in this cartoon here. For left-handed circularly polarized XUV light, for instance, and right-handed circularly polarized light, you would see the photoelectron ejected on one side or another side of the sphere. And this technique has actually very high sensitivity. So this is the technique we have chosen for our experiment. The experiment has been performed in collaboration with the group of Yann Merest and Valérie Blanchet in Bordeaux, from Bordeaux. So basically, we investigated methyl-lactate, which is a molecule used also in our muscles for the metabolism. And here you can see basically the scheme of the excitation. We use multiphoton resonant excitation. In this case, is 2+1, so 2 UV photons to reach a manifold of Rydberg state, and then 1 IR photon to ionize the molecule. These are the two enantiomers of methyl-lactate with an indication of the chiral center. And this is actually the UV spectrum used in our experiments. As you can see, it's quite a broad spectrum because indeed we have short pulses and therefore we don't have much of energy selectivity. This is what we have to live with. But it's actually very well centered in the region where we want to do this 2-photon excitation. Then we basically send the UV pump, as I said, to excite the molecule, and the near probe pulse has been properly manipulated in polarization in order to obtain this circular polarization, which is necessary to probe the chirality, as I was explaining. And we were measuring in the velocity map imaging spectrometer the momentum distribution of the photoelectron, as you can see here. So basically, the PECD can be calculated by measuring this momentum distribution of the photoelectron for circularly left polarized light and circularly right polarized light, and then making the difference divided by the sum of this signal. And then you obtain these trays, as you can see here, where you have negative and positive signal, which is due to this directionality of the photoelectron emission, as I was explaining before. And here you can see the two enantiomers with the opposite sign, as you would expect, of course, due to the opposite chirality, indicating that this is indeed a real PECD signal, so it's not a fake or an artifact due to this subtraction that we do. The very interesting result here is that the PECD is indeed measured as a function of the delay between the UV pump and the IR probe pulse is actually changing in sign on a quite short time scale and resulting in a sort of periodicity, and which we are still interpreting, but potentially assigning to a competition between different states involved in the process. So here I'm just showing the extracted beta parameters from the photoelectron angular distribution, beta 0 and beta 1. Here you have on top of the slow femtosecond, the long femtosecond response, if you subtract this slow response, then you're left with peculiar oscillations in both the beta 0 and the beta 1, which results also out of phase. This is also another interesting aspect of this measurement. So as I said, there are still ongoing calculations in collaboration with the group here in Bordeaux, and we don't have a final interpretation yet. But what is very interesting is that it seems indeed by the calculation of the transition moments that both the state HOMO and HOMO -1 are involved in the first step. Such that we could have indeed an interference between electronic states, so could originate these oscillations. We could not exclude, of course, the involvement of nuclear dynamics, which is, of course, another level of difficulty in the calculation to be introduced. Finally, still I have, I think, a few more minutes. I would like to show just preliminary results we have obtained in water clusters. So the idea of my group is that to slowly move to a more realistic environment for these biorelevant molecules. So we don't want to study isolated molecules in the gas phase, but we would like to insert these molecules in a water environment. And this can be done, of course, by investigating, for instance, liquid jets, but this is a high level of complexity. So there is some intermediate step that can be done. And this is, for instance, by putting the molecule in a cluster of water molecules. So we started by the investigation of the simple cluster of water molecules, and this was done in collaboration with the group of Ruth Signorel at ETH. Again, we measured the photoelectron angular momentum distribution, the same apparatus as I was showing before. This is XUV only ionization with long pulses for the moment. So here you can see a comb of harmonics and the resulting EMI spectra. In the target, we have a mixture, a natural mixture of H2O clusters and monomers, because we have also water in the gas phase, as well as the carrier gas for the clusters, which is helium. So the first challenge is to recognize the presence of the three in the results in order to isolate the contribution of the cluster. So we measured these angular distributions, as I said, and we were already able to see a difference between the distribution of the monomers and the cluster, with a clear shift, which is expected because of a change in the IP and the ionization potential. And then we performed some calculations in order to fit our electron spectra with a signal coming from the monomer only, which is the blue one, and the cluster. And by fitting our spectrum, we obtained a size of the cluster corresponding to about 100 molecules of water, which is also corresponding to what is expected from this calibrated source, indicating that we are indeed identifying the contribution of the clusters, and that we have a mixture of 50% water in gas phase and 50% clusters. And we are now performing time-resolved measurements from which we did not have extracted yet any final information, but we are looking forward tracing some dynamics in there. With that, I have concluded. I would like to just thank all my group in Hamburg. If you want to know more about our activities, you can visit our website, atto.cifel.de, and all my international collaborators, and you for your attention. Thank you. I can't hear you, Agnes.
Okay, can you hear me?
Yes, now yes.
Okay. So thank you very much for your nice talk, very interesting talk. And as I can see, there are two so far. There are more. There are at least 3 questions. The first question comes from Emily Zaire. She has a question about the C60. As you compare to neon, I understand that you are making the assumption of a single EWP, but in C60, doesn't you have collective effect? It could be in the form of the giant resonances.
Yes, I think this is actually more or less the point, in the sense, if I understood properly the question. In order to extract the signature of the giant resonance, which is actually expected to result in the Wigner delay, we need to have a sort of absolute clock. And this is actually provided by neon, which is a very well-known reference target. So by performing this subtraction, we actually are left with the contribution of only the Wigner delay induced by the presence of the giant resonance, and of course, as I said before, the delay induced by the IR induced dipole, which is also contributing in the delay of the photoemitted electron. I hope I have answered the question.
Okay. The second question comes from Hans Jakob. In your interpretation of the adenine 2 plus signal, why do, oh, sorry, jump my windows. Why do the other shake-up states, which are populated much faster, not or negligible contribute?
Yes, they of course, they also contribute a bit, but this channel I have shown is actually basically favorable because, as you can see from this lumoplastic state, there is a huge absorption of the IR probe pulse. And this we also have assigned it probably to a charge dynamics, because this lumo plus 6 is a state which has quite a delocalized charge. So as soon as you populate the state, you can see a sort of charge inflation, which is not happening with the other states. This is actually increasing the cross-section for the absorption of the IR probe field. And this we have observed it in the calculation by including the IR field, that we could see that indeed the IR was very much absorbed by this state.
Okay, thank you. And then there is another question, still from Hans Jakob. What information do you hope to extract from the water cluster studies compared to our recent publication on liquid water? Maybe you know science.
Yes, so I think your investigation was a very nice investigation of the electron scattering dynamics in liquid water, and indeed I think we should first of all try to see clusters are in a way in between molecules and condensed matter. It's a kind of bridge, so they might well behave as a liquid jet, or they might have a slightly different dynamics as well. Plus, it's, let's say, as I said, more work in progress, in which we would like more to insert molecules inside these water clusters. So the aim of this study, okay, this is just at the beginning. So we are starting with the source, which is injecting these large water clusters. But we would like also to investigate molecules in the water clusters. With the water clusters, we can also adjust the size, so we can go from very small clusters to large clusters. And I said we can study the bridge between the individual molecules and the condensed matter. That is what you have observed, of course, in the liquid jets. So yeah, I mean, of course, your investigation is the final investigation in water, as it is in a liquid, and we would like to more study this bridge between the molecular phase and the condensed matter phase.
So there is no more question, no more official question in this Q&A panel, but may I ask you something in concerning to the first part of your talk? You remember the collaboration with the group of Angel Rubio. Do you know what kind of theoretical method they used to corroborate your experiment?
In Adenine, so we collaborated with them for the Adenine experiment, and they were basically using at the beginning TDDFT just to investigate the fragmentation dynamics. So I was not showing this. Eric Masson will show this in detail in his talk. So there is a calculation of the bond elongation, and therefore the breaking of the molecule. So this is predicting what we observed, that you should get a high percentage of fragmentation. So TDDFT is to calculate the bond elongation. And then they were using the rate equations, as I said, just for making a simple estimation of the transition times of these shake-up states involved. Then the other big calculation, which was done with a more sophisticated approach based on the Green's functions, this was done by the group in Rome. So Gianluca Stefanucci and Enrico Perfetto, and they collaborated with the group of Angel Rubio as well.
Okay. Okay, thank you very much. Thank you again, Francesca. This nice and very interesting talk. And then we can move to the next speaker. Thank you.
Okay, thank you.
Thank you. I would like to introduce the next speaker. He is Ladislav Nagy from Babes-Bolyai University, and the title of his presentation is holograms of atoms and molecules obtained with the photoelectrons induced by ultra-short laser pulses. So please.
Good afternoon to everyone. I hope you can hear me. So my talk is about the holograms of atoms and molecules obtained with photoelectrons induced by ultrashort laser pulses. And I have done this work together with my former students, Attila Tóth and Zsolt Kis, and my colleague, Sándor Borbély. Well, it is well known that if a strong laser pulse ionizes an atom or a molecule, the electron is driven back towards the residual ion. And this electron may rescatter on this residual ion. And the rescattered electron wave may interfere with the direct wave, which is not rescattered. The idea that this interference may form a hologram traces back to 2004 in a paper by Spanner and co-workers. They had this idea, and this picture is from their paper. The first experimental observation of this hologram was done in 2011. Huismans and co-workers have published in a science paper about a measurement on metastable xenon atom. They have used the 7 micrometer wavelengths laser. And they have obtained this hologram, which is shown here. And these radial fringes, which nowadays are called a spider-like pattern, are a consequence of the interference between the direct and the scattered wave. Many theoretical studies have been published since then. For instance, there is a recent review paper of Figueira de Morrison, Faria, and co-workers, where I would like to cite what they write in the last section of their paper, which is very important to our cost action. There is a shift from merely structural questions towards the aim of steering electron and core dynamics in real time. I would mention also some other papers. For instance, XUV and co-workers have analyzed the different interference types, the subcycle interference dynamics for atoms. Bayan and Bandrock have published a paper about attosecond time-resolved imaging of molecular structure, mainly about backwards rescattering on H2+. Marco Hertelt and co-workers have studied the molecular dynamics of H2 and D2, focusing also on backscattering. Meckel and co-workers have a paper about the strong field photoelectron holography for nitrogen molecule. And finally, I would mention the paper of Porat and co-workers about the attosecond time-resolved photoelectron holography. This is an experimental and theoretical study. Well, let's move to our calculations, which is ab initio calculation. We solved numerically the time-dependent Schrödinger equation for one electron in the field of the laser pulse and the residual ion. And we applied the time-dependent close coupling method for the discretization of the radial wave functions, the finite element discrete variable representation method was employed, and the propagation of the wave function is time is done using the short iterative Lanczos method with adaptive time step control. We use in our calculation 2-cycle attosecond XUV pulse with 100 nanometer wavelengths. And this 2-cycle, as you see on this image, is a cosine-like pulse. So it is a symmetric pulse. It was demonstrated that cosine-like pulse emphasis this subcycle interference, which forms the hologram, and suppresses the intercycle interference. So we are focusing on the subcycle interference, which forms this hologram. In the following, I will show you what we have obtained for the time evolution of the wave packet and the transition probability for the hydrogen atom. We represent the transition probability as a function of the momentum of the ejected electron. And in the following images, you will see the following. Here, on the left up corner, you see the transition probability, or more exactly, the density of the probability density of the electron in momentum space as a function of time. Here we will follow the time. Here you see the same density in coordinate space. And here you will see the total ionization probability as a function of time. If we are at the beginning of this pulse, where the intensity of the electric field is very low, practically the total ionization probability is negligible. And you see that here practically we have a dipole-like structure of this electron probability. This is because here the one photon ionization dominates. If we go further, of course, when the electric field is more intense, this dipole-like character disappears, and the electron cloud moves downwards, both in momentum and coordinate space. And after that, of course, when the electric field changes sign, it starts to be driven back to the target. And here, when this wave packet rescatters on the target, it interferes with the direct wave, which is not rescattered, and you see this very characteristic interference pattern. Of course, when we go further, this interference pattern changes, and when we arrive to the end of this pulse, practically we obtain the final hologram, which in principle can be detected experimentally. So we observe very nicely this spider-like hologram, and this hologram is more intense in the forward direction, so we mainly analyze the forward rescattering. We have also analyzed how the density of the interference fringes depend on the field intensity. Here you see on figure A, we have a very high intensity, 1 atomic unit of the maximum electric field, and down to 0.1 atomic units. What is very easily observed that when we move from high intensity to low intensity, the density of these radial fringes is decreasing. And we can also link this density of the fringes to the maximum distance between the electron wave packet and the core when before it is rescattered. This maximum distance we denoted this with Z0. And of course, for higher intensity, Z0 is larger, and for lower intensity, this Z0 is lower. And what we can state is that when this Z0 maximum distance is larger, in that case, the density of the radial fringes is larger. Now we have analyzed also how the hologram depends on the scattering potential. So we have performed our calculations for different atoms besides the hydrogen, also for helium, neon, and argon. First, what we can observe is that helium and argon has similar ionization potentials. Like helium and neon have higher but also similar ionization potentials. And if we represent the ionization probability as a function of time, of course, this ionization probability depends on ionization potential. So if this ionization potential is lower, then the ionization probability increases more rapidly than for helium and neon. Here on the lower panel, we have represented the mean distance of the electron from a target as a function of time. And of course, the Z0, which is the maximum distance, is larger for the two atoms which has lower ionization potential, so for hydrogen and argon. So we can expect that hydrogen and argon, because they have a larger Z0, they will have a more dense interference pattern. Here you see this interference pattern for the four studied atoms. So first we can observe that for hydrogen and argon, this density is a little bit larger than for helium and neon. But of course, we can observe also important differences between hydrogen and argon and helium and neon. So the interference pattern does not depend only on the ionization potential, but depends also on the shape of the potential. For better analysis, we have represented here the ionization probability density as a function of the ejection angle of the electron for a fixed momentum. And you can observe here that for argon and neon, the interference fringes are denser than for helium than for hydrogen and helium respectively, because of the deeper potential. So the ionization potential is the same, but if the potential is deeper, then the rescattered electron will have a larger accumulated phase. Now we have studied also the hydrogen molecular ion. And here we have performed calculations in prolate spheroidal coordinates. The details of these calculations you can see on poster 16, which will be presented this afternoon. If we want to analyze molecular effects in this hologram, we can compare our molecular results with two central models with the same ionization potentials. And we have constructed two spherical models for this molecule. For this potential, is it practically charged sphere, and this is another model where we have also an exponential dependence. What you can observe here is that the two spherical models practically have the same pattern, but we have some slight differences between the molecular model and the central pattern. In order to analyze in more detail these differences, we have represented again the ionization probability density as a function of ejection angle for a fixed momentum 1.5. And we have made this representation for three internuclear distances, 1, 2, and 4 atomic units. Of course, the equilibrium distance is 2 atomic units, but we wanted to analyze how this pattern depends on this internuclear distance. What can be observed immediately is that we have larger differences between the molecule and the central potential for backward scattering, in accordance with this paper, which was already mentioned at the beginning of my presentation. We represent the same thing for more cases, for momentum 0.5, 1, 1.5, and 2, and for the three studied internuclear distances. Beside the fact that we observe that for backward scattering there is a larger molecular effect, we can observe here that for large momenta, also in forward scattering, these minima are much deeper for molecule than for the atom. We have also represented for the backward scattering a fixed angle of 180 degrees ejection of the electron. The ionization probability as a function of momentum of the ejected electron for the three studied internuclear distances. And what is observable that for all three internuclear distances, we obtain here a minimum for the molecule, which is not observable in the central field potential spectrum. And I think that this is a clear trace of the two-center interference, in spite of the fact that the location of this minimum cannot be predicted by a simple model. In a simple model, the value of the momentum for this minimum should be proportional with 1 over r. But this is not exactly proportional, but you see that this observed minimum moves to lower momenta as the r increases. And the other minimum which is observed in the forward direction, this minimum is observed along the first spatial interference minimum. So the blue curve is the molecular spectrum, and the red curve is the central potential. Here you see a clear minimum, which may be a trace of two-center interference. However, we do not observe this two-center interference very clearly at all the possible places, because this interference pattern are in many cases washed out by the interference of electron waves created at different time moments of the laser field. So we can draw some conclusions. First, we have performed time-dependent Schrödinger equation calculations for reproducing the hologram of different atoms and H2+ produced with a two-cycle XUV pulse. We have analyzed mainly for the hydrogen atom, but also for other atoms, the dynamics of the interference pattern. We have shown a clear influence of the target's potential on the hologram. And for the H2+ molecule, we have observed a difference between the hologram of the atom and the molecule, but this difference is not essential, so it is only a slight difference. And we have observed that the interference pattern due to the two centers of the molecular target is barely observable. It is washed out probably by temporal interference. Thank you for your attention.
Thank you very much, László, this interesting and nice talk. And as I check, there is no question, but I would like to ask you that would it some sense to do this kind of simulations for larger system, let's say diatomic molecule, but with many or more, not only one electron, but with what would be the possibility and difficulties, and please comment on it.
Well, our program solved the Schrödinger equation for one electron. So with this method, we are capable to deal only with movement and dynamics of one electron. Sure, we can try also for other molecules, but at this stage only with one electron approximation. So if we want many electron dynamics, then we will need other methods. So this method cannot be applied for many electron dynamics.
Mm-hmm. And do you know experimental group where this kind of experiment are performed today, or?
Well, this kind of hologram was put in evidence experimentally by the group of Vacher. Mm-hmm. The first paper was in 2011 in Science published. But that was for infrared pulse, and our calculation is for XUV pulse. I hope that there will be some group who will do some holographic imaging also with XUV pulse, but at the moment I don't know.
Okay, so if there are no more questions, then I would like to thank again this interesting talk, and then we will go further. Thank you again, László.
Thank you.
The next speaker will be Dudovich from Weizmann Institute, Israel. And then the title of her talk is Attosecond interferometry.
Okay, can you see my talk?
Yes, I can. Yeah, I can see you.
Okay, thank you very much. And it's a great pleasure to participate in this meeting. I'm sorry that I cannot do that.
I'm sorry, Nirit. Would you mind sharing your screen again? It's not visible at the moment. Thank you.
So thank you very much again, and it's a great pleasure to participate this meeting. In my talk, I will describe how we can take two very important measurement schemes in Attosecond spectroscopy, most importantly in high harmonic spectroscopy. One of them is subcycle gating, where we tweak a subcycle phenomena with attosecond precision. The second one is attosecond interferometry. And as I will describe in my talk, once we integrate the two concepts together, then we're able to obtain a direct insight into the quantum nature of strong field phenomena. But let me start by first thanking my wonderful group at the Weizmann Institute, and also close and ongoing collaboration we have with many years with the Max Born Institute in Berlin, Bordeaux University, the Politecnico in Milano, and with Daisy in Hamburg. So attosecond science, as we heard several times during this morning, led to a true revolution in our ability to capture extremely fast phenomena in nature. And over the past 2 decades, attosecond spectroscopy really enabled us to reveal a large range of strong field mechanisms, starting from the very basic process of field-induced tunneling, and then to Hall dynamics or charge migration in small molecular systems, all the way in recent years to extremely fast currents in solid state targets. Now we are able to reveal these phenomena and follow their evolution in time due to the very basic mechanism of attosecond pulse generation process. And as described already this morning by Katerina, and I'm sure most of you are familiar with this process, attosecond pulses are generated during a 3-step recollision mechanism that we are all familiar with. And in my opinion, one of the most beautiful aspects of this mechanism is the ability to directly transfer the coherence of a strong laser field into the coherence of an electronic wave function that interact with the field, and then upon recollision, back into the coherent properties or the optical properties of the emitted attosecond pulses. And one of the main challenges in this field is the following question. This is, I think, a question that triggered the imagination of many people in the community. Can we take the emitted radiation and find some clever way that enable us to trace it back such that we obtain a direct insight into the attosecond scale evolution of the electronic wave function as it interacts with a strong laser field? One approach is, let's zoom at the optical cycle of the strong laser field. And if we find a way to apply a gate is any kind of subcycle manipulation that really tweaks the optical cycle with subcycle resolution. We can either tweak the instantaneous amplitude, the instantaneous polarization, or even the phase. And now if we find a way to somehow shift this gate within the cycle, then we obtain attosecond precision of the strong field phenomena induced by this field. A completely different approach zooms at the emitted attosecond radiation itself. And here we understand that the amplitude, but most importantly, the phase of the emitted radiation encodes valuable information about the strong field dynamics induced by the laser field. However, in order to retrieve this information, we have to find a way to perform some interferometric measurement. And in my talk, I will review both branches and finally show how we can combine them together. Let me start with subcycle gating, looking at really one of the most basic strong field phenomena, and this is field-induced tunnel ionization. Tunneling really, I think, set the starting point for attosecond science. It's the first step in many of the experiments that we look at. And the most simple case to consider is adiabatic tunneling, where the electron tunnels through an almost static barrier, where the barrier itself is dictated by the instantaneous value of the laser field. Therefore, in this case, we understand that at the peak of the laser field here, the barrier is strongly suppressed and tunneling probability is relatively high. However, a few hundred of attoseconds later, the barrier lifts up, tunneling probability drops to 0. So the entire mechanism evolved during a small fraction of the optical cycle. And one question that we asked ourselves several years ago is, can we apply a gate that will resolve the temporal evolution of the instantaneous tunneling probability? Can we see the drop in the instantaneous probability due to the oscillation of the laser field? Well, in order to do so, we had to look for a gate, and a very simple gate to consider would be a second harmonic field, which is parallel, polarized parallel to the strong fundamental field. And this field can be orders of magnitude weaker compared to the strong fundamental field. However, if the two fields are in phase, then in this case, the barrier is slightly suppressed, enhancing the tunneling probability. And if the two fields are out of phase, then we slightly lift the barrier and therefore suppress the tunneling probability. Eventually, this information, the tweaking in the tunneling probability, is mapped by the recolliding electron into the amplitude of each harmonic order that we observe in our lab. However, the tweaking itself, the change in the ionization probability, crucially depends on the moment at which the electron is born. For example, if the electron is born at the peak of the laser cycle, then here the perturbation doesn't do much because the tunneling probability is relatively high. So we will observe modulation, but they will be rather weak. But if the electron is born later within the cycle, where tunneling probability is relatively low, here a weak perturbation can lead to a dramatic effect, inducing really substantial modulations in the tunneling probability. So now let's go harmonic by harmonic and observe how they respond to this weak perturbation. With this measurement, we're able now to trace the experiment back and follow the change in the instantaneous probability during the optical cycle. So here is a schematic picture of what we measure. This is a window within the cycle. Within this window, the barrier slightly lifts up, and this tiny change in the barrier leads to a dramatic fall in the instantaneous tunneling probability. And subcycle gating enables us to resolve such dynamics. Now, once we go from atoms to molecules, here we realize that tunneling serves not only as a very accurate temporal event, but also as an extremely accurate spatial probe. For example, tunneling from a molecular orbital projects the outer part of the orbital into the structure of the electronic wave function, which is ionized. And an interesting situation is tunneling along the nodal plane of the orbital. In this case, for example, the phase of the ionized electronic wave function can change dramatically across this nodal plane. And one question we ask ourselves is, can we resolve this phase variation? Eventually, this phase is in the harmonic, and all we have to do is think of a clever experiment that will enable us to interfere these two parts of the electronic wave function. Right? Naively, what we would like to do is take two ionization direction along this direction and that direction, and then find some way that will enable us to interfere them. If we can interfere them, we can project back their phase and then say something about the symmetry and the structural properties of the molecular orbital. Now, unfortunately, we cannot directly perform such an experiment. However, we can use subcycle gating in order to manipulate electron trajectories and then interfere them together. So let's use almost the same manipulation that we have used before, second harmonic field, but this time it's polarized orthogonally to the strong fundamental field. With this configuration, we can really tweak the instantaneous polarization of the laser cycle. And now we are able to shape our electron trajectories. We can define what will be the angle of ionization and angle of return, and we do that for the first half cycle, but we have exactly the same manipulation for the second half cycle, just inverted. It's a mirror image of this manipulation. Eventually, we cannot avoid that the two contributions interfere together in the high harmonic spectrum, and we can think of this experiment as a two-arm interferometer. However, as long as we have here some isotropic systems, such as aniline molecules or atomic systems, then the interferometer is quite boring, simply because it is balanced, simply because the two arms really encode the same information. However, once we go from atoms to molecules, then here the situation becomes much more interesting. Now we unbalance the interferometer and we really probe the molecule from two very different directions. So let's think of a certain configuration. We set the delay such that ionization angle is the same. It is ionized along 0 degree. However, recollision angles are substantially different. So this trajectory probes the electron almost at 0 degree, while the other electron probes the molecule at almost 90 degrees with respect to its main axis. This can be viewed as an interference between two projections of the molecule, 0 and 90, and what we interfere here is really the transition dipole moment at the moment of recollision. We can now change a two-color delay and induce a completely different interferometer. Once we change the delay, now we have the same recollision angle. It's both at 0 degrees. However, the ionization angles are dramatically different. Here, the electron tunnels at 90 degrees. Here, at 0 degree, of course, it's all schematic. And therefore, we understand that now we interfere two very different tunneling events along two different directions of the molecular axis. So in the lab, we performed this experiment with CO2 molecules, and we recorded both interference event as a function of the alignment angle of the molecules. So we are able to reconstruct the recollision transition dipole moments, amplitude and phase for CO2 molecules as a function of alignment angles. And then we are able, by changing our interferometer, to perform the same reconstruction, this time for the tunneling event. So indeed, we observe the nodal plane here around 0, which is associated with a quite substantial phase shift around 0 degree of almost pi. Okay, so far we have induced subcycle gating to manipulate and probe strong field phenomena such as field-induced tunneling. In the next experiment, we will go from the strong field regime into the completely other regime, weak field one. Let's look at one of the most basic quantum mechanical phenomena, which is photoionization, already introduced in this meeting. Photoionization is extremely important since it projects the quantum state of matter into free electrons that we can directly measure. And attosecond signs enable us to visit and measure single photoionization with attosecond precision. And one question we ask ourselves is, since we have seen that recollision is such a valuable tool and we can manipulate it, can we use this tool in order to probe with extremely high sensitivity and accuracy the origin of single photon transition? Naively, the answer is no, since recollision is induced in strong field environment, which doesn't look to be the proper tool to probe weak field transition. However, if we look again at this very basic recollision mechanism, we understand, as many other people in the community understood, that photoionization is already there. It's there at the moment at which the electron returns to the parent ion and emits a single photon. In fact, we know that photoionization and photorecombinations are really the opposite mechanism of each other. They are described by almost the same transition dipole moment, and they capture the same dynamical properties. However, there is one important difference between the two. In photoionization, we produce electron. We can resolve the phase of electron by performing, for example, a rabbit measurement, and rabbit measurement resolves the phase derivative also associated with the group delay. However, once we switch from electron to photons, then the problem becomes much more natural because we have direct access into the phase of photon. All we need is an optical interferometer. And while in rabbit we can resolve phase derivative, we do not have a direct access into the phase of each individual spectral component. Switching to photon provides us with direct access into the phase associated with each spectral frequency. So in this measurement, I will switch from subcycle gating into attosecond interferometry. Now, conceptually, the idea is very simple. All we have to do is to build an interferometer of 2 attosecond sources. Of course, in the lab, it's a non-trivial challenge because we have to stable this interferometer with attosecond precision. And indeed, it took us several years to obtain that. And here's a schematic description of the interferometer. We start by focusing intense laser field into some gas jet. We produce a train of attosecond pulses. The two fields co-propagate. They're reflected from a 2-segment mirrors. Focus again, and here we generate a second source of attosecond pulses. Eventually, the two sources interfere in the high harmonic spectrum. And one of the most beautiful observations that we obtain is a really trivial one. We manipulate the relative delay with this 2-segment mirror, and what we observe is the following. We see that each harmonic number, this is 17, this is 19, 21, beats, and it beats according to its fundamental frequency. So we see slow beating of 17 harmonic, and then faster and faster beating rate as we go to higher and higher harmonics. And as we control the delay, we go from constructive to destructive interference, constructive again, and so on. So now we have an attosecond interferometer, which enables us to extract for each harmonic number, both its amplitude, but most importantly, the phase information, which cannot be directly obtained. And we have started by looking at the interference between two really simple systems, helium and neon, and here helium can serve as a reference frame, providing a relatively flat spectral phase. So what we do interfere here are two photorecombination events that can be considered as two photoionization events. And here is phase as a function of harmonic order. And what we can see is that the phase itself is almost flat, which means that there are no delays here. Rabbit cannot extract any time delay associated with photoionization. However, there is a significant phase shift here, which is directly associated with the different symmetry of the two different wave functions. But once we go to slightly more complex systems, such as argon, although it's not really complex, we see that the phase changes much more rapidly. For example, in this spectral regime, we can observe the well-known signature of the Cooper minimum of argon. Okay, so far I have described two completely different approaches. We can either do strong field control, strong field manipulation by applying a subcycle gate, or weak field control by building an interferometer. Towards the end of my talk, I will show that we can really combine them together. We can integrate them, and here introduce attosecond gated interferometry. And in order to demonstrate this idea, let me go back to the problem that we have started with, field-induced tunneling. So far, we have considered a relatively simple case where the electron tunnels through a static barrier, adiabatic tunneling, where the barrier is dictated by the instantaneous value of the laser field. However, if we increase the Calegari parameter described here by either reducing the field intensity or increasing the fundamental frequency, eventually we go into the non-adiabatic regime, and the electron feels the oscillation of the barrier as it tunnels out. Okay, so it is excited as it propagates under the tunneling barrier. And this excitation leads to tunneling with some initial energy, initial velocity, as many people have measured in the lab. So in this case, the electron is born with some extra velocity, but the exit point itself is shifted towards the origin. There is another interesting difference between the adiabatic and the non-adiabatic case, and this is captured by the phase of the electron. The electron would be born with some extra phase that it accumulates as it propagates under the barrier. And this phase is really valuable because it really encodes the information regarding the dynamics of the electron under the barrier. So if so far in high harmonic spectroscopy, we perform phase measurement in order to say something about the propagation of the electron in the classical regime, in the continuum, here the question is, can we use phase information in order to reveal the propagation or the evolution of the wave function under the tunneling barrier? In order to do so, we need two important components. One of them would be subcycle gating. We have to somehow tweak the interaction with subcycle resolution. So let's use the same approach we have used before. I'll add a weak perturbation. And if the two fields are in phase here, what we will do is slightly suppress the barrier. We can slightly enhance the barrier. And this, as we have seen in the first experiment, will modulate the instantaneous ionization probability, okay, simply because we tweak the barrier. But a more interesting manipulation to apply would be to shift the second harmonic field such that it is pi/2 with respect to the fundamental field. Here, the barrier is not shifted. However, we influence the instantaneous gradient, the temporal modification of the gradient. Okay, so here the rate of change has been modified. As a result, the non-adiabatic interaction itself can be either suppressed or enhanced. What would be the outcome of this manipulation? It can be captured in the phase of the tunneled electron. So here what we will observe are phase modulation. Here we maximize the non-adiabatic interaction, and here we suppress it. And not surprisingly, the two should be pi/2 out of phase with respect to each other. But if we want to fully reveal this complex information, now we need an interferometer. It's not sufficient to look at the amplitude of the harmonics only as we did before. This information, of course, is mapped into the amplitude and phase of the emitted harmonics by the recollision mechanism. So let me integrate Attosecond interferometry in order to reveal the complex phase and amplitude information. So here's the experiment. We combine the two together, we apply a gate, and let's fix it. So now the gate is fixed at a certain position, and we perform Attosecond interferometry to resolve this phase. So this axis controls the XUV delay and observe phase modulation. And here, this is the gating position. So we resolve one phase, and now we sweep the gate within the optical cycle. And each position of the gate will repeat the interferometric measurement and resolve a single phase. And this is a 2D measurement of, for example, harmonic 11. We do that for all harmonics in our measurement. And if we zoom into this measurement, we observe that indeed the phase slightly oscillate as we change the gate. Those oscillations are direct outcome of the excitation of the electron under the barrier. It cannot come from any other origin. And here we extract this phase oscillation, and we see those beautiful oscillations. So with this measurement, we are able now to trace back and extract the phase of the electron right here at the exit of the tunneling barrier. And we see a phase shift of about 1 radian, which agrees very well with stationary phase approximation prediction. What we can also do is take one step further and extract the exit point and its modification by the excitation. So the red line is the adiabatic prediction. And this is their measurement. We can see that there is a significant shift of about 1 angstrom towards the origin. And this shift is again predicted by the theoretical stationary phase approximation. So with that, let me conclude. Many of the experiments that we perform lies at the interface between strong field interaction and ultrafast phenomena. Subcycle gating on interferometry enable us to reveal these processes. But really, I think the most exciting and important direction to take would be to integrate those fields of research with solid state physics. And as many people in the community already demonstrated, the strong laser field can induce significant modification to the band structure, changing the basic properties of a solid state material. And our dream would be to bring all those tools that work really beautifully for atoms and small molecules, and then, for example, watch how the band structure itself changes within less than 1 optical cycle. And I believe that subcycle gating would enable us to observe that. We already have some preliminary results, or even dream further and think of multi-electron effects such as subcycle, mode transition, or topological phase transition. And with that, I would like to thank you for your attention.
Thank you very much, Nirit. This was very interesting and nice. And then as I check the question and answer panel, there is no question at the moment. So maybe we can wait, or I can ask, but I am not in that field. So this is just a question that you can see a clear fingerprint in the phase, whether it was a non-adiabatic or adiabatic, yes, the tunneling. Can you see that?
Sorry, can you repeat the question?
You can see in the phase, the clear fingerprint that
yes.
the process at the beginning was not non-adiabatic or adiabatic.
Yeah, so the phase measurement that we perform and I discussed towards the end of my talk is really a fingerprint of the non-adiabatic transition. And we observe that as we increase the Keldysh parameter, this phase increases and vice versa.
Mm-hmm. It's very interesting. Okay, so still no more question. So thank you again.
Thank you very much.
And then we go to the last talk, this session. The last speaker is Morgane Vacher from University of Nantes, France. And the title of her talk is How Nuclear Motion Affects Coherent Electron Dynamics in Molecules. So please, Morgane, start.
Thank you, Agnes. Let me start by sharing my screen.
Yes, it's okay.
Yes, it works. Okay. Hi, everyone, and thank you again, Agnes, for the introduction. For those who don't know me, my name is Morgane Vacher. I am a theoretical chemist, and I've been working on simulating electron dynamics in molecules. So today I will give you an overview of our results. Most of the results I will show you are from my PhD, which I've done at Imperial College London. After that, I've done a postdoc in more traditional photochemistry, and now I am a CNRS researcher at the University of Nantes. Started to work again on attochemistry. So as you know, about 20 years ago, the first Attosecond pulses were generated, and they have two interesting, important properties. First, they're very short duration, but also because of the time, energy, uncertainty principle, they are large spectral bandwidths. And because of this large spectral bandwidth, when you excite or when you ionize an atom or a molecule with such a short pulse, you populate not only one, but several electronic states. And here on the right-hand side, I'm showing the simple example in the case of an ionization that would populate coherently the ground and the first excited state of the cation, forming what we call an electronic wave packet. So in experiments, we are able to generate, populate simple or more complex electronic wave packets. This arises a number of questions. For example, in a given experimental setup with a given attosecond pulse, what is exactly the electronic wave packet that gets generated? Then we know that this electronic wave packet is non-stationary. So it evolves with time. And how exactly does the electron move in the first few attosecond or femtosecond after this sudden ionization? Does it interact with the outgoing electron, between the outgoing electron and the cationic electronic wave packet? Or within the cation, how does the electron and nuclei interact with each other? Is the electron dynamics affected by the nuclei of a molecule? And going beyond the observation of electron dynamics, can we actually use this electronic wave packet to induce then a new type of chemical reaction? So myself, I got interested in the questions that are in red, and I'm going to show you, explain and present you the theoretical method that we have developed over the years in order to address these questions. And other theoretical developments have been more focusing on the description of the continuum states in order, for example, to determine very accurately the exact electronic wave packet that gets populated upon sudden ionization, or the interaction between the outgoing electron and the cationic electronic wave packet. So if you want, you know that if you want to determine how electrons move upon photon ionization, you need to solve the time-dependent Schrödinger equation. So for the moment, considering only the electronic degrees of freedom, you need to solve this time-dependent Schrödinger equation with the electronic Hamiltonian here and the electronic wave function. For conceptual understanding, it's enough to consider as a simple electronic wave packet a superposition of two states, which I've shown you on the previous slide, and this is a time-dependent electronic wave packet where you see the complex phase factors here that involve the eigen energy of the electronic states. And the quantity that may be more physically relevant is the time-dependent electronic density that you obtain by multiplying this by its complex conjugate and integrating over all but one electron coordinate. And this is the expression that you get, that you can express using these electronic density metrics, or more explicitly like this. With here on the first line, you have the state-specific electronic densities weighted by the population in the two corresponding electronic cationic states. These are time-independent, while the cross terms in front of the electronic transition density is here time-dependent. We have cosine oscillations with a period inversely proportional to the energy gap between the populated eigenstates, and the amplitude of these oscillations are proportional to the product of the population between the two eigenstates. And you can also express this oscillating terms as a sum of the off-diagonal element of the density matrix, which are called the electronic coherences. So you know that because of some interference effect, when you populate a time-dependent electronic wave packet, you can obtain oscillation in the electronic density. And in order to apply this to a given atoms or molecule, the ingredients that you need to compute, that we need to compute, are the electronic eigenstates and the electronic eigen energies. And this, the field of quantum chemistry have been developing a number of electronic structure methods to allow you to calculate in an approximate way for a given molecule their electronic states and energies. So we can apply it to molecules. And here I'm showing an example by the group in Heidelberg, where you see a hole initially created on one localized site of the molecule, which migrates to the other site, to the amino group in 4 femtosecond, and then comes back with a oscillate between these two sites with a total period of about 8 femtosecond. And here I'm showing another example that you've seen already in some slides before this morning. And this is just to show you that it's not always as simple as this, with a hole well localized on one site and migrating to another site. And depending on the electronic wave packet that you create, how many states, but also, and importantly, the nature of these states, if they are localized or delocalized. The oscillation that you predict in the electronic density may be very significant or not. So now what happens in a molecule when you consider not only the electronic but also the nuclear degrees of freedom. So simply looking at this, if we imagine adding some nuclear dependence here, I mean, you know that the electronic states and electronic energies will depend on the nuclear geometry. So the nature of the oscillating density and the period of it will also depend on the nuclear geometry. But there are also more complex things that can happen. Because of the coupling between electronic and nuclear degrees of freedom, you can induce non-adiabatic relaxation. So number one, change in the electronic population. You can also, because the nuclei are not localized, but they are described by a nuclear wave packet, you can imagine that a dephasing of the oscillation across the within the nuclear wave packet width. And number three as well, the nuclear wave packets on the different electronic states may evolve in different direction, and this will decrease the overlap between the two. And all of these three processes may lead to damping of the oscillation in the electronic density. This is what we call the decoherence of the electronic system. And then the question has been how important these three mechanisms are in molecules in general. I mean, to what extent, on what time scale do they occur, and then to what extent do they affect the oscillating motion in electronic density. So we've been developing methods to address these questions. This is only a slide with equations, so just bear with me for these slides. Here we want to consider the entire molecule. So this is a time-dependent Schrödinger equation with the molecular Hamiltonian and the molecular wave function. But as we do in quantum chemistry, we usually start by splitting the electronic and nuclear degrees of freedom. So we first consider the electronic Hamiltonian and the electronic time-independent Schrödinger equation to obtain the electronic energies, eigenvalues, and electronic eigenstates. As I told you, this is using a given electronic structure method. You may know acronyms like TDDFT or ADC we heard this morning. And then we use these electronic eigenstates as basis to express the total molecular wave function. These coefficients are then the nuclear function. They are time dependent. And these are the ones, this is then the equation of motion that we need to solve for the nuclear function to describe the time evolution of the whole molecule. And here we get back and we put back the coupling between electron and nuclei with this lambda here, which couples nuclear function on different electronic states. And a key difference between the method that I bore to describe the coupling between electron and nuclear dynamics is the description of this nuclear function. So one set of methods are the grid-based methods on the left-hand side, for which you express then the nuclear function on a grid, and then you numerically integrate the equation of motion. So this is quite convenient. However, that means you need to pre-compute and fit the potential energy suffixes before you can actually run the dynamics calculation. And then you run into the problem of the exponential scaling of the basis set size with the number of degrees of freedom. So these approaches are usually limited to a few number of degrees of system and relatively small methods. An alternative to go to larger molecules is to use trajectory-based methods. The idea here is that you have basis function that evolve with time. You make them move in such a way that they adapt and describe as best as possible the time evolution of the nuclear function. And that allows you to minimize the basis set size that is needed. So that's nice, but you need to make sure, of course, that you have enough basis function in your basis set to be converged. It also can be a bit more intuitive because it's a bit more classical like. And an important advantage is that because of the local character of the basis function that we use, typically Gaussian functions, you don't need to pre-compute and fit the potential energy surfaces before the dynamics calculation, but you can generate them on the fly. And that allows you to go to larger dimension. And that's the type of methods that I've been developing and using. So there are actually many flavors of trajectory-based methods. You may recognize some acronyms or some names here. The simplest methods are on the right, surface hopping and Ehrenfest, for example, while on the left-hand side, the DDVMCG method allows a full quantum mechanical treatment of both the electron and nuclei. So it's more accurate. And most of the results I'm going to show you in this presentation are using the Ehrenfest method and a few of them with the DDVMCG methods. So here, this is just to show you examples of molecules that we've been looking at, so the type and the size of the molecule that we can treat. So polyatomic molecules. In this presentation, I will show you examples, results mainly from the top row, molecules in the top row, but we can also study molecules with nitrogen and oxygen atoms and coupled, diverse coupled chromophores. So the first results I would like to share with you are actually pure electron dynamics simulations, so at a single fixed nuclear geometry, not taking into account the effect of the nuclei on this family of molecules, benzene, toluene, paraxylene. And this is to illustrate that the fact by using a chemical substitution, by adding methyl group in different places, we are able to basically tune the position of the equilibrium geometry of the neutral species with respect to the cationic state. And that means you're able to tune the energy gap at this specific geometry at which you ionize the system. You tune the energy gap between the populated eigenstates and therefore the time scale of the electron dynamics of the oscillation in the electronic density. In benzene, you arrive directly at the degeneracy points on no electron dynamics, and as you add one or two methyl groups, you have to pay attention where you put the methyl groups. You may also affect the nature of the electron dynamics. In this case, we affected only the time scale of electron dynamics, making it faster and faster. And this we found in several examples that we could do this tuning of electron dynamics using a chemical substitution. For example, in this other family of molecules here, adamantate cage with two methylene group on the side from which we ionize the molecule. And by playing with the adamantate cage, more precisely by changing the number of carbon atoms in the ring in this cage, we are able to induce either fast or slow electron dynamics. And this could be, I think, useful knowledge to know how to do this in the future when we want to design and maybe use electron dynamics. So now to actually show you some results about the effect of the nuclear motion. I'm comparing pure electron dynamics on the top row with Ehrenfest trajectories on the bottom row, so with the nuclei moving for, on the left-hand side, toluene, and on the right-hand side, paraxylene. And what you see is that in toluene, after 3-4 femtoseconds, you start to see a difference between these two plots in both the nature and the time scale of the oscillations. While in paraxylene, it gets a bit faster here. Here we go back to 0, while here we are at the minimum of the oscillations. But the effect is much less important in paraxylene. And we looked at the effect of nuclear motion in a number of molecules, and the rule I think that we can extract from our studies is that the faster the electron dynamics, the smaller the effect of the nuclear motion. And that makes sense because the faster the electron dynamics, the larger the energy gap is, and therefore the further away you are from a region of non-adiabaticity, therefore the smaller the coupling is between electronic and nuclear degrees of freedom. And so we saw this for these benzene molecules, but also, for example, in the adamantane family of molecules. On the top, you have the very fast. So in solid lines, this is a simulation with fixed nuclei, and dashed lines, this is a nuclei moving, and see that when the electron dynamics is very fast, they are almost superimposed. We don't almost see the difference, while where the electron dynamics is very slow, then the effect of the nuclear motion is very big. Now, I think one maybe of the most significant contribution that we've made to the field is when looking at the effects of the nuclear delocalization, the fact that the nuclear wave packet is delocalized over space, considering an ensemble of nuclear geometries, fixed nuclear geometries, or an ensemble of Ehrenfest trajectories. This is for paraxylene, where the effect of the nuclear motion itself was actually small, comparing a single electronic simulation on the top and an ensemble of electronic simulation in the bottom with each of the purple line representing one electronic dynamics simulation. So it's very important to consider enough geometries in new ensemble to actually converge the description of the nuclear wave packet. And the white line corresponds to the average, and you see that on average we have an ultra-fast dephasing of the electron dynamics oscillation. And depending on the molecules, I mean, we've looked at several of them, and this dephasing half-life occurs from about 5 here to 10 femtosecond. I think BMA maybe the one we observed for which we had the longest dephasing or coherence half-life with about 10 femtosecond half-life. And so it's a very important effect, and it's therefore very important to understand it. And for this, we developed, we proposed a very simple analytical model that is able to relate the coherence half-life and some physical property of the system, such as the nuclear wave packet width and the relative slope between the populated states. And therefore, if we want to understand it or to control it and try to have an effect on it, it's important to understand where it's coming from and how we can affect this. So far, I've shown you the result with the Ehrenfest method. The Ehrenfest method is able to describe the non-adiabatic transition between electronic states, so the change in population. Is able, with an ensemble of geometries or trajectories, it's able to describe the dephasing mechanism between the different phase wave packet components. But it is a mean field approach, which means that the nuclear wave packet on different electronic states are not allowed to move away from each other. And I was a bit worried about this with this mean field approximation and the effect that it could have on the coherence lifetime. So we decided to run some more accurate, more expensive, but more accurate simulation using the DDV-MCG method, where here we treat quantum mechanically all electrons and nuclei. I don't have time to go into the details, but what I can say is that our fully quantum simulation have confirmed the ultra-fast dephasing of electron dynamics on the same time scale as we predicted with the semi-classical, quantum classical method, and also confirmed that the dephasing mechanism plays an important role in the decoherence. Before, the last part I would like to talk about is actually not on the electron dynamics that is influenced by the nuclear motion, but the same, simulating the same process, but looking at it from the other side and looking actually at the nuclear motion that is induced by the electronic wave packet. And here I'm taking as a reference the nuclear motion that is induced by a single adiabatic state. So in BMA, if you populate only D0 or D1, for example, it corresponds to ionizing, removing an electron from this orbital, and the nuclear motion that is induced is a stretching of this carbon-carbon double bond as you remove an electron from pi bonding orbital. This blue curve here corresponds to the average carbon-carbon bond length between the two sides, while the cyan line here, which is 0, corresponds to the difference between the two bond lengths. And you see that here, because we have a symmetric hole that is stationary, then you induce a symmetric stretching of the double bond. And as we populate an electronic wave packet, one thing that we do is that we localized the hole on one side, which means that even if on average the stretching is the same, now the difference in bond length, it doesn't stay 0. There is one bond that stretches more than the other, starting from by this one. And because this hole is also non-stationary, then we see oscillation in this asymmetry of the stretching. I don't know if you can see in your screen, but here I'm reminding the oscillation of the electronic dynamics in gray. And you see that the oscillation in the asymmetry, in the difference in bond length, matches the oscillation in the electronic dynamics. And this is what we call charge-directed reactivity. So I don't want to go into detail here, but this is just to show and to mention the fact that by manipulating the exact composition of the electronic wave packets, and here I'm changing the phase of the two states that gets equally populated, you change where the electron hole starts and where it goes and how fast it goes there. And this way you control, on the right-hand side, you control the asymmetry of the nuclear motion. But of course, if you want to do a more realistic simulation and you simulate an ensemble of trajectories, you will find, not very surprisingly, that as the electron dynamics decays with time, also the asymmetry in the stretching that you induced eventually disappears, and you see the two curves that, the oscillation in the two curves that are damped with time. So in summary, and here I'm summarizing basically the key results of my presentation, but maybe the most important message is that we have developed theoretical tools that enables us to simulate electron dynamics in molecules, which means connecting the electronic and nuclear degrees of freedom. And I think this is crucial for the future developments of atochemistry, where the aim will be we'll try to aim at inducing a new type of photochemical reaction, populating a particular electronic wave packet. With this, I would like to end by thanking the people involved in this work at Imperial College London, but also my new host team in Nantes, and thank you for your attention.
Thank you very much, Morgane. It was really very interesting talk. And then I check again the question and answer panel. There is no question. Maybe I would like to ask, are there any experimental works corroborate this very nice theoretical works, what you have done?
If there are experimental works on anything there, or can you repeat the question? Sorry.
Are there any experimental works? Do you know some experimental works which are corroborate with this theoretical calculation what you have done, or do you know some experiment?
Well, I think we are yeah, I mean, I think these experiments are very challenging. I mean, observing, I mean, I'm sure experiments that have observed charge migration, and these experiments are very difficult because either you observe something that is very indirect compared to the charge migration, such as the fragmentation yield, or you have very, for example, now it's still difficult to perform attosecond per attosecond probe experiment.
I know that.
Yeah. So I think this is still challenging, and going beyond this, going to the control of chemical reactions. This has been done on small diatomic molecules, but to be done on a larger molecule, no, I'm not aware of such works. But I'm sure this will come, and then we need to be prepared theoretically to help both in the choosing the electron, the molecule, and the experimental setup, so that it's successful.
Yes, I know this very well because we had many problems with the ozone from experimental side. You know this maybe from Benjamin, and this was very interesting work, but the experiment is horribly difficult. Yes. Okay. Okay, there are questions. It's good. I should see it because it's too small. First comes from Johan Cooper. In Tulane, the internal rotation of the CH3 has huge effect on electronic properties, like transition moments rotate by plus minus 30 degrees for the CH3 rotation. How do you take such things into account or observe in your electron dynamics? This question was from Johan Cooper.
Okay, so the first thing I can clarify that in our simulation, we don't take into account the ionization itself. Okay, so we assume that we assume the exact composition of the electronic wave packet. So we don't take this step into account, but what we do is we sample the vibrational state of the ground state, which means that in principle we sample a different configuration with the rotation of the CH3 groups. And if this has an effect on the electronic structure, then we'll see the effect on the corresponding transition density and therefore the oscillation. And I think this is why when we make the average, just by making the average at t equals 0, the amplitude of the oscillation decreases because of the blurring of the different properties when you rotate around the CH3 group. I don't know if I answered the question.
There is another question from Amelie Zer. My understanding is that you are assuming sudden ionization. I guess this is valid if you indeed use an Attopast to do this and then populate multiple cation states. How short would recon the pulses should be?
Indeed, I mean, I'm not taking into account the interaction between the outgoing electron and the cationic species. How short does it need to be? I'm not sure, but I mean, you're probably familiar with a simulation that the group in Madrid have performed, where they compared the electron dynamics in the cation, treating or not the outgoing electron. I don't remember exactly the duration of the pulse that they used in their simulation, but the effect was quite small, and their conclusion is that it was not significant. But of course, that depends on the duration of the pulse, but also how, the energy of the pulse, to know how long it stays around the cationic species.
Okay, so meanwhile, the third question arrived from Hans Jakob. You mentioned the limitation of Ehrenfest dynamics, not accounting for the different forces in different electronic states. Would it be possible to run separate trajectories in different states? Of course, the challenge would be how to incorporate the electronic wave packet in such an approach. Are there attempts in this direction?
So, I mean, if we want to keep the methods, theoretical methods simple, and we want to do mixed quantum classical trajectories, there are two limiting cases. These are the Ehrenfest method and the surface hopping method. And the Ehrenfest method, because you have this mean field treatment, is not that you actually don't take the individual forces into account, but you take the average of them in addition to the coupling. But you take the average of them. On the other hand, we have the surface hopping methods where you're either on one surface or the other, and therefore you take only one of them and you don't take into account the coupling. So, and there are also groups that simulate electron dynamics and take into account the nuclear motion semi-classically using the surface hopping methods. Both of them have disadvantages, and the one I see for the surface hopping is that you don't take into account the coupling between the two states in your nuclear motion, and this will have an effect. I mean, the coupling is the key effect if you want to do atochemistry. If you want to induce a particular nuclear motion, thanks to the fact that you're populating electronic wave packets, whereas we have this effect in Ehrenfest methods.
Thank you. What's that? Okay, again, I think Gilbert Grell, I should thank you for the interesting, Thank you for the interesting talk. Can you guess or do you know whether the electronic dephasing time of 5 to 10 femtosecond will be a valid estimate for wider range of system beyond those that you have studied?
I think this is a time scale, yes, of dephasing time. I mean, there have been after our simulations, there have been other groups that have estimated the coherence half-life using other methods and looking at other molecules, and they seem to be, I mean, consistent with our results, even if they use different approaches in different molecules. This 5, 10, I mean. This is the order of magnitude of the coherence that several groups, not only us, have been founding.
Okay, and then one more comment, not a question, from Amelie. Excellent presentation, Morgan. So thank you. And then I would like thank you again, Morgane, to this interesting talk. And then, as there are no more questions, we are closing slowly this second session of this conference. I would like to thank all the speakers again for the valuable and interesting presentations. And now I encourage you that the speakers will be available in the meet and speaker session immediately. After this session, hopefully, but somebody maybe will go to eat for lunch, but you can discuss there. And the next session, scientific session, will start at afternoon, 3 p.m. So thank you again. Bye-bye.